Okay, let's move on with our course. In the last class, we have looked at the Schrödinger equation for the hydrogen atom, and we discussed also the solutions of the Schrödinger equation. Now we saw that the solution is a wave function that has three quantum numbers: the quantum number n, the quantum number m, and the quantum number L. So now we only need to insert these quantum numbers into that general solution of the Schrödinger equation, the respective wave function, in order to calculate the explicit states that the electron can adopt. These states are also called the orbitals. So when we say that an electron is in an orbital, then we actually mean that the electron is in a particular state, and that state is described by a wave function, which is a three-dimensional wave function because it has three coordinates x, y, and z. So now let us go through that step by step, and let's begin with the most simple orbital, the 1s orbital. So you are probably all familiar with the 1s orbital. So we talk about a 1s orbital when the quantum number n is equal to 1. The quantum number L is equal to 0, and the quantum number M is also equal to 0. So when we plug in these numbers into the general solution for the Schrödinger equation, then we arrive at the wave function for the 1s orbital. So as you probably all know, 1 stands for the quantum number n, which is equal to 1, and s means sharp. When we have an s orbital, then we always mean that the quantum number L is equal to 0. So you see here the general form, or the explicit form, of the wave function for the 1s orbital. So you see that the overall wave function is a product of the angular parts of the wave function. Okay, so that's basically the azimuthal part multiplied with the colatitude part, and that angular part of the wave function is then multiplied with the radial part of the wave function. So let us look first at the angular parts of the wave function, the angular part of the wave function, and we see that the angular part of the wave function is only a simple number, or the product of two simple numbers, which again gives a simple number. Namely, it's 1 over the square root of 2 pi times 1 over the square root of 2. Okay, so that gives a simple coefficient. So that means that our orbital is angle independent. Okay, it doesn't depend on these two angles chi and theta at all. And that implies that our orbital is being spherical. So a 1s orbital is spherical. You probably all know that, but this is the reason why the 1s orbital is spherical. The angular parts of the wave functions are only simple numbers. So now here you see the radial part of the wave function, and you see that this radial part of the wave function is an exponential term. Okay, so you see here a coefficient 2 over a0 to the power of 3 over 2 times e, and that's the Euler number, to the power of minus r over a0. Okay, so that tells you that the amplitude of the wave function for the 1s orbital exponentially declines, okay, with, according to the term e to the power of minus r. So that means that the amplitude of the wave function exponentially declines as we go from the nucleus further away from the nucleus until we are eventually infinitely far away from that nucleus. So this is actually shown here by this red curve. Okay, So here we see the radial wave function. R is the function of the radius in units A0, and I will talk about that in a moment, what A0 means. But we see here that the amplitude of the wave function exponentially declines as we go away further from the nucleus. So now, what is A0? So A0 is nothing else but the Bohr radius, and the Bohr radius is nothing else but the first radius of the electron in the hydrogen atom. And we calculated that Bohr radius previously. It was 5.29 times 10 to the minus 11 meters. Okay, so that's the radius of the electron, of the orbit of the electron when the electron is in the first orbit. So after all, that's just a unit, but it's useful to give the radius in these units because it relates to something familiar, which is the Bohr radius in the classical Bohr atom. Okay, so now let us look at what this result means for the probability to find the electron at a particular point in space when we consider our electron as a particle again. Remember, it's insufficient to only consider the electron as a wave. It also, of course, still has particle properties. So now you need to remember that the square of the wave function represents the probability to find the electron at a particular point in space. So now, as the amplitude of the wave function exponentially declines with increasing radius, that also means that the square of that wave function exponentially declines with increasing radius. So that means that the probability to find the electron at a point in space is highest the closest to the nucleus or directly of the nucleus, and we can indicate this by plotting or depicting the probability to find the electron at a particular point in space by a density of points, and this is shown here. Okay, so you see here in this depiction of the 1s orbital that the density of points is the highest directly at the nucleus, and it exponentially declines as we go further away from the nucleus. So that's also interesting in the context of the question that Rutherford already raised, right? So why is the atom mostly empty space? And why don't atoms actually collapse? Now, this quantum mechanical picture, in a sense, gives you the answer, well, the atom is actually collapsed, okay? Because the probability to find the electron at a point in space closest to the nucleus is actually the highest. It is just that due to the wave properties of the electron is not found only, well, very close to the nucleus. With some probability, you can also find it further away from the nucleus, but that probability exponentially declines. So now there's another aspect to that. So we can certainly talk about the probability to find the electron at a particular space, but we can also ask the question, what is the probability to find the electron at a particular distance from the nucleus? And that's actually a different question. Okay. Now the distance because now we have to integrate over all the points in space that are at a particular distance from the nucleus. Okay, so all these points in space now lie on the surface of a sphere that has that particular radius. And of course, the surface of the sphere increases with the radius. So the greater the radius, the more points in space you need to consider. Okay, and therefore, in order to get the probability to find the electron at a particular distance from the nucleus, you need to multiply the square of the radial function with the formula of the surface of a sphere. Okay, and this formula for the surface of a sphere is 4 pi r squared. So that means now that you multiply this exponential term here with a term in which r to the power of 2 appears. Okay? So that means now that when r is equal to 0, the entire radial probability function becomes 0. Okay? And that means that the probability to find the electrons at a distance closest to the nucleus is actually 0. However, it will increase as you go further away from the nucleus, okay, as the amplitude increases with r squared. So that effect is somewhat offset by the effect of the exponential term, okay, which tends to decrease the amplitude of the wave function as you go further away from the nucleus. And the result of that is that, well, when you see this in this curve here, that the radial probability function first increases, okay, goes to a maximum and then decreases. So that means nothing else that as we go further away from the nucleus, the probability to find the electron at a particular distance from the nucleus increases first, goes to a maximum, and then declines. And then the radius, which is represented by this maximum, is basically the radius at which the probability to find the electron is the greatest. Okay, so now it's interesting to look at what that radius actually is. And that radius here is exactly the Bohr radius. Okay, so now that has also interesting implications, because it says, well, Bohr didn't include the wave properties of the electron in a Bohr model, but in a sense, he was still right, assuming that or calculating that the electron would be found at the Bohr radius, at the distance of the Bohr radius from the atom. It is just that the quantum mechanical model now gives a refined picture, saying that, well, because of the wave properties of the electron is not only found on the Bohr radius, it's just found with the greatest probability on the Bohr radius. Because of the wave properties of the electron may also be found further away from the nucleus or closer to the nucleus, but the likelihood is just not that large. And as we go very close to the nucleus or infinitely far away from the nucleus, that probability becomes 0. Okay? So now that is also interesting in the context of defining the size of an orbital, because this radial probability function here approaches 0, but it actually never becomes 0. Therefore, even at very large distances from the nucleus, there's still a probability to find the electron, even though that probability may be very small. So given that, how do you define the size of an orbital? And the accepted definition is to define the size of an orbital as the, well, volume in which the probability to find the electron is 90%. Okay, when you see this depicted here on the left side of the slide, you depict commonly a 1s orbital as a sphere, and the radius of the sphere is defined, well, by the probability to find the electron with a 90% probability somewhere in between that sphere, which is defined by the particular radius. So now this is the quantum mechanical interpretation of the 1s orbital. Now let us move on from the 1s orbital to other orbitals. Let's first go to the 2s orbital. So now when we talk about a 2s orbital, then the quantum number n is equal to 2. Because it's a s orbital, the quantum number L is still equal to 0, and the quantum number m is equal to 0. So again, when you plug in these quantum numbers into the general solution for the Schrödinger equation and calculate, you arrive at the wave function for the 2s orbital, which is shown here. So again, let us analyze this wave function. So again, it's a product of the angular part of the wave function with the radial part of the wave function. You see again that the angular part of the wave function is just a simple number. It's again just 1 over the square root of 2 pi times 1 over the square root of 2. So that means nothing else but that the orbital is angle independent, and for that reason the orbital must be spherical. So let us look now at the radial part of the wave function, and you see it is actually 3 components. This one here, which is a simple coefficient, okay, that's just 1 over 2 times the square root of 2 times the Bohr radius, which is also a constant, to the power of 3 over 2. Then we have, again, this exponential term here, the Euler number to the power of minus r over 2a0. But in addition to that, we have now this term here, to minus r over a0. Okay? So now, what implications does that have for the orbital? The main implication is that the orbital now has a node, and that node describes the surface of a sphere, hence that node is called a spherical node. Okay, why is that? Now, when we just look at the exponential term here, well, again, the orbital or the wave function would just exponentially decline as we go further away from the nucleus. Okay? But now, because of this part here, the wave function will become 0 when 2 minus r over a0 is equal to 0. Okay? And that is the case when r is equal to 2a0. Okay? Because then 2a0 over a0, well, that gives 2, and 2 minus 2, well, that gives 0. Okay? So that means at this distance from the nucleus, 2 over a0, our wave function will become 0. And at this point, it will change actually its algebraic sign. Okay? So at radii smaller than 2a0, the amplitude of our wave function will be positive. At 2a0, it will become 0. And after that, it will become negative. Okay? Go here through a minimum, and then approach 0 again. Okay, so now that point here represents the surface of a sphere that has the radius 2a0, and this sphere is called a radial node or spherical node because on the surface of that sphere the amplitude of the wave function changes its algebraic sign. Okay, now this is this is depicted again here. Okay, so very close to the nucleus, our wave function has a positive algebraic sign, but then at a particular distance from the radius, the amplitude becomes 0 and changes algebraic sign, and further away from the nucleus, it becomes the algebraic sign becomes negative. Okay, so now what again about the probability to find the electron at a particular point in space and at a particular distance from a nucleus? Okay, so you see again here that very close to the nucleus, the amplitude of the wave function is at the greatest, so the probability to find the electron basically very close to the nucleus is still the greatest. Okay, then it declines, then we go through our node, and then here the amplitude again increases, it's just negative. But remember, the probability to find the electron at a particular point in space is equal to the square of the wave function. So the square of a negative amplitude also gives something positive. So this again gives a positive probability that goes through another maximum. And then the probability to find the electron at a point in space again becomes smaller again and eventually approaches 0. Okay, now what about the radial probability function? In order to get the radial probability function, we must multiply the square of the wave function with the surface of a sphere, 4 pi r square. So if we do that, then you see that we're actually getting a curve that goes through 2 maxima. So very close to the nucleus, the probability to find the electron is 0 because of the r squared term. Then we are going through a small maximum. So here where the node is, again, the probability is 0, must be because the amplitude of the wave function is 0. And then the probability increases, and we are going through a second very large maximum of probability here. And then the radial probability function declines again and becomes 0 as we go infinitely far at the nucleus. So the difference to the 1s orbital is that we have 2 maxima. This is imposed by the node instead of 1 maximum. And generally, the probability to find the electron is higher further away from the nucleus as compared to the 1s orbital. That means that when we depict the 2s orbital as a sphere, that 2s orbital has a larger radius in comparison to the 1s orbital. Okay, now let us go from the 2s orbital to the 3s orbital. So now for the 3s orbital, n is equal to 3, L is equal to 0, m is equal to 0. So you see here the explicit form of the wave function for the 3s orbital. So again, you see that the angular part of the wave function is just a simple number, and that means we would expect our 3s orbital to be spherical again. So let us have a closer look at the radial part of the wave function. which is described by this term here. And again, this term can be separated into three parts. So this one here, which is simple coefficient, okay? Then we have again here our exponential term, e to the power of minus r, now divided by 3, a0, and this term here. So this term here is 27 minus 18 r over a0 plus 2 times r squared over a0 squared. So you see that this term has the format of a general square function of the type ax squared plus bx plus c. Okay. Now c in this case would be 27. Okay. B in this case would be minus 18, and a in this case, well, so it would be minus 18 over a0. Sorry. And a would be 2 over a0 squared. Okay. So now this term here defines two spherical nodes for the 3s orbitals. Okay, because there are now two possibilities for this term here to become 0. And when this term here becomes 0, then the overall wave function becomes 0, because this term here is multiplied with this term and with that term as well. So now if you wanted to find the exact radii at which the wave function becomes 0, then we could solve, well, this square function here according to that general formula for the solution of a square function. You're probably all familiar with that. So when we have a general square function of this shape here, we can find the positions at which fx becomes 0. So this term minus b plus minus b squared minus 4ac over 2a. Okay, so there are always two solutions. Okay, because there are two solutions, we have two nodes for our 3s orbital. Okay, so now you see here in this graph again how the wave function overall behaves. So very close to the nucleus, again the amplitude is the highest. Okay, then we get here this exponential decline. Then we have here our first node where the amplitude becomes 0 and changes its algebraic sign. Then we go here through a minimum. Then we further go up back to 0, where we have now our second node. Then we go through another maximum here until eventually the amplitude of our wave function becomes 0. Okay, so that means that again, in terms of probability, the probability to find the electron at a particular point in space is the highest, the closest to the nucleus. Okay, but then we have here a second maxima, and here we have a third second maximum, and here we have a third maximum. So now what about the radial probability function? So in order to get that, we have to multiply r squared with the formula of the surface of a sphere, 4 pi r squared. Okay, and then that gives here now this curve. Okay, so now again very close to the nucleus, the probability is 0. Then we go through a first maximum. So here where the first node is, again the probability is 0. Then we go here through a second maximum. Then here we have our second node. Again here the probability is 0. And then we go here through the largest third maximum. And then our probability declines further and becomes eventually 0 as we go very far away from the nucleus. Okay, so overall the probability to find the electron is higher further away from the nucleus in comparison to the 2s orbital and the 1s orbital. For that reason, we would depict our 3s orbital even larger in comparison to the 2s orbital. So this is a general trend. As we increase the quantum numbers n in the s orbitals, the orbital size becomes larger. So you see here again depicted by color the algebraic signs of the wave function. Initially, the algebraic sign of the wave function is positive, indicated by this orange color here. Then it becomes negative in that area of radius, indicated by the blue color, until it eventually becomes positive again. Okay, so we note that the 3s orbital has 2 spherical nodes. Okay, now of course we could go to the 4s and the 5s orbital and so forth, but nothing would change, but that we would have more spherical nodes to consider. So there is not a lot new to learn here. So for that reason, we now leave the s orbitals and instead look at p orbitals. So the p orbital with the smallest quantum number n is the 2p orbital. And for that now we need to consider 3, because for a p orbital, which has the quantum number L is equal to 1, there are 3 allowed quantum numbers ml. Okay, so that's 0 for the pz orbital, +1 and -1 for the px and y, respectively. So now if we plug these quantum numbers here into the general solution for our Schrödinger equation and calculate the wave function explicitly, then we will get, well, the wave function for the 2p orbital, and you see here the wave function for the 2pz orbital. Okay, now let us first look at the angular part of the wave function. So now you see that we do not have only simple numbers anymore. One of the 2 angles, actually theta, appears here. And that means our orbital is now angle dependent, and that means that it cannot have a spherical form anymore. It must be somehow non-spherical in nature. Okay, we will talk about this in more detail in a moment. But before that, let us first look at the radial part of the wave function. Okay, now we see that the radial part of the wave function has 2 components here, 3 components, this one here, which is a simple coefficient, then our exponential term again, e to the power of -r over 2a0, and this one here, r over a0. So this term here produces an important difference to the s orbitals. It means, or it implies that when we look at the probability to find the electron at a particular point in space, that it's not the highest at r equal to 0 anymore, because at r equal to 0, due to this term here, the entire wave function becomes 0. Okay, so that's an important difference to the s orbitals. So in fact, when we look at the amplitude of the wave function, then we start out at 0, and that's indicated here by the dotted lines, go through a maximum, and then our wave function declines in amplitude again. Okay, at smaller r values, this term here is dominant. Okay, that's why we first get this increase, and at larger r values, our exponential term becomes dominant and then leads to the decline of the amplitude until it finally approaches 0. All right. So what about the radial probability function. So the radial probability function is the square of the radial function times the sphere of a radius, the surface of the surface of a sphere with a particular radius r. And you see that the shape of this curve is quite similar. So very close to the nucleus, our radius is equal to 0. Then our radius increases. It goes to a maximum and then finally goes down to 0 again. Okay. So now to the question, if our orbital is non-spherical anymore, which shape does it have then? And in order to answer this question, it is helpful to convert the angular part of the wave function from polar spherical coordinates back into Cartesian coordinates. Okay, and when we do this, then this product here becomes this term here. Okay, a half times the square root of 3z over pi times r. Okay, so this term now defines a so-called a planar node, which is a form of an angular node, which defines the shape of the orbital. Okay, we can ask, well, under which circumstances will this term become 0? Because if this term becomes 0, then the entire wave function becomes 0. Okay, well, if z becomes 0, well, then obviously the entire wave function becomes 0. So in three-dimensional space, where we have 3 coordinates, x, y, and 0, what defines this condition geometrically? Okay, so now z is only 0 in the xy plane. Okay, in the xy plane, x can adopt any value, y can adopt any value, but z would have to stay 0. Therefore, now the xy plane defines a node within that orbital. Okay, you can say that the xy plane is an angular node because it's imposed by the angular part of the wave function. Because it has the shape of a plane, we can call it a planar node. Okay, so because if it's a node, the algebraic sign of the wave function must change at the node. So above the xy plane, okay, the amplitude of the orbital must be different than below the plane. Okay, and that basically explains the dumbbell shape of the 2pz orbital, right? It points into z direction, okay, because the xy plane defines a planar node. And above the plane, the amplitude of the wave function must be different than below the plane. Okay, overall, our pz orbital will point into z direction. All right, now we have discussed the 2pz orbital. Now what about the other 2p orbitals? Okay, so we have the px and the py to consider. So the wave function for the 2pxy is given by this form here. Okay, so let's look first at the angular part of the wave function. You see again, it's angular dependent, but now not only the angle theta appears, although the angle chi appears here. Okay, and px and py is only different by this algebraic sign here in front of this imaginary number here. It can be either plus or it can be minus, depending on whether we talk about the px or the 2py orbital. But overall, again, we clearly see that our wave function is angle dependent, so it can't be spherical in shape. So the radial part of the wave function is exactly the same as for the 2pz orbital, so there's nothing in addition to consider here. We only need to investigate the angular part of the wave function further to see, well, how does it affect the shape of the orbital? So to do that, we again convert the angular part of the wave function from polar coordinates to Cartesian coordinates. And then this product here becomes this term for the px orbital and this term for the py orbital. Okay, for the px orbital, the term is a half times the square root of 3x over pi times r. And for the py orbital, the term is a half times the square root of 3y over pi times r. So now, let us look at this term first. So this term becomes 0 when x is equal to 0 and x is equal to 0 in the yz plane. Therefore, for the px orbital, the yz plane defines a planar node. Okay? And that, again, defines the dumbbell shape of this orbital, pointing now in x direction. Okay? And to the left of the yz plane, the algebraic sign of the wave function must be different in comparison to the right of the yz plane. So similarly, for the 2py orbital, this product here is 0 for y equal to 0, and y is equal to 0 in the xz plane. For that reason, the xz plane defines the planar node within the 2py orbital. Okay, in front of the xz plane, well, the orbital must have a different algebraic sign than behind the xz plane, and within the xz plane, well, the amplitude of the wave function becomes 0. So this explains why both the py and the px orbit have also dumbbell shape, but they point into the x and the y direction, respectively. Okay. So now we have explained the shape of our 2p orbitals. We can now next look at the shape of a 3p orbital, and we are considering in this case only the 3pz orbital, because the 3px and the 3py will just work analogously, just the orientation of the orbital will be different. So here's the wave function for the 3pz orbital. So you see that, again, the angular part of the wave function is angle dependent, it depends on the angle theta. But now for the radial part of the wave function, in addition to the exponential term and the term r over a0, which still exists, you have this term here, 6 minus r over a0. Okay, so this term here defines now a spherical node. So in comparison to the 3p orbitals, which didn't have a spherical node, the 3p orbital actually does have a spherical node. So at which we can also very easily calculate at which position the node is. Well, it's at 6a0, because at 6a0, this term here becomes 0, and when this term becomes 0, then the overall wave function becomes 0, okay? 6a0r over a0, well, that gives, well, 6 r, and 6 minus 6r, that gives 0. Okay, that means that, well, we have a spherical node to consider. So you see here again the plot for the amplitude of the wave function. So at r equal to 0, the amplitude is 0 because of this term here, and then goes to a maximum. And then here at 6a0, it changes its algebraic sign because of this term here, becomes negative, and eventually the exponential term becomes completely dominant. Because of that, our wave function approaches 0. Okay, now what about our radial probability function? Well, that's r squared times 4 pi r squared. So very close to the nucleus, probability is 0. Then we go to a first maximum. So here where the spherical node is, we again have 0 amplitude. And then we go here to a second maximum until our wave function finally approaches 0. Okay, so now what about the angular part of our wave function? Well, the angular part of our wave function again implies a spherical node. So we could convert it into Cartesian coordinates, and we would see that it's only a function of z. So when z is equal to 0, that part of the wave becomes 0, and z is only 0 in the xy plane. So that means that in addition to our spherical node, which is shown here, okay, we have also a planar node in the xy plane. Okay, so our orbital has still a dumbbell shape, which is characteristic for p orbital, but the algebraic sign changes, well, more often because of the existence of the spherical orbital in addition. Okay, so here you see it's positive. So here at this surface of the spherical node, it changes to negative. Then here at the planar node, it again changes back from negative to positive. And here at this part of the spherical node, again, it changes back from positive to negative. All right. Now, let us move from the p orbitals to d orbitals. And I see we're a little bit short of time, but we can at least start with that already. Let's start with the 3dz square orbital. You can see here the formula or the wave function for the 3dz square orbital. So see here the angular part, and here you see the radial part. You see that the angular part is a function of an angle, theta in this case. So we would expect a non-spherical orbital. Here you see the formula for the radial part of the wave function, and you see that it's composed of this simple coefficient here, r squared over a0 squared times this exponential term here, e to the power of minus r. So now, because of this term here, at r equal to 0, the amplitude of our wave function is 0, and it's then increasing until basically this exponential term overpowers this term, so that our curve goes through a maximum and then declines until it eventually becomes 0. So the radial probability function has a quite similar shape. So initially, the probability is very small. Then we are getting an increased probability going to one maximum, and then our probability declines until it eventually approaches 0. All right, let's turn our focus to the angular part of the wave function. In this case, the angular part of the wave function defines what is called a conical node. We can again see that when we convert that angular part of the wave function from polar coordinates to Cartesian coordinates, then this term here becomes that term here, of course omitting all the mathematical steps necessary to do that, which would go way beyond an inorganic chemistry class. And you see that the angular part of the wave function is now a function of 2z squared minus x squared minus y squared. And mathematically, this describes a cone. So now when does that term become 0? Well, it will become 0 when 2z squared is equal to x squared plus y squared. Okay? And that describes the cone. Okay? Therefore, our 3D z-square orbital has this characteristic shape here. You see here two cones that are separating the two orbital parts that have different algebraic signs. Here, these two lobes on top, above and below the xy plane, which have the same algebraic sign, in this toroid here, which is opposite algebraic sign. All right, I see we are out of time, and we'll discuss the other d orbitals in the next class.